Okay, good evening, good morning, wherever you are. Welcome back to Python for Orbital Mechanics. My name is Husseina Etti-Balogun, but you can just call me Kenny. Actually, today I'm going to start with the end of what we did last week, which was a simulation of the two-body problem, and I couldn't find the reason that I had the bug last time, so I found it, and I want to show you what the bug was because it was a very, very stupid bug. Um, Let me try and share that. Have you guys tried to run the code by yourselves? Okay, so I'm not sure if I added these colors during the class, but like in my spare time I was just tinkling, so I decided to change the color of the background and the color of the bodies themselves. So I changed the color of the background to pink, and then the color of I was trying to do like different colors for the bodies, but I couldn't figure it out. So both of them ended up dark red. But anyway, the main problem I had the last time was I didn't put these two brackets. So I was running the file and it would have the draw function, the screen would show up and there would be no movement. So I just want to show you how that looks like, how it looked like. Um, Okay, so this is what it looked like. It was just a plain screen. That's what I was seeing. Um, but let me close this now. If I restart, will it still go back? Close window. Um, yeah, so if you don't do like me and you actually close the function, save the file, then redo it. Yeah. Now can we actually see the the function running? So this is what it's supposed to look like when you just do two bodies with the two body file text file txt file that we created. Um and in the assignments there were other simulations that you could do like the three body, n body, whatever you wanted to do. So I just wanted to show that before I started for this week. Okay. Okay. So yeah, welcome back again to the second week of this 5 week cohort. So last week, as I was saying, we simulated the two-body problem, but we didn't fully go into the mechanics of how we did that. We just brushed over the solution of the problem itself. And today we're going to be talking about what goes into an orbit. So we will look at the six orbital elements, sometimes called the classical orbital elements or the Keplerian elements after Johannes Kepler that came up with them. I tried to do it, but it's looking for the universal pi file in the pi. Mm, yes. So Samuel, this issue might be because you haven't CD'd like in your terminal. You didn't change directory into the code folder. So you know there's the Pi for orbital mechanics folder, and inside that there's a code folder, and inside the code folder is where the universe.py um file is. So you have to make sure that you CD in the terminal into the code folder before you run it, or else it won't work. So try that out and let me know. Okay, um so last week we explained about the origins of Kepler's three laws of planetary or orbital motion. The first one being that all orbits are ellipses with the central body at a focus. So the periapsis, which is the furthest point in the orbit from the body, are the apoapsis, which is the closest point in the orbit to the center of the body. So here, this is what we would call the periapsis, the furthest point uh that the body could possibly make from the focus. And then here is the apoapsis. So these two are joined by a line called the line of apses. So this line is what we'd call the line of apses. If we stretch this line, we see that the orbit would increase. So let's say we hold these 2 points and we just stretch them. The orbit size would increase. So this shows us the first parameter when defining our orbit, which is size. It's indicated by half of the major axis. So from here to here is what we normally call the major axis. Um, and then half of this is what we would call the semi-major axis. So the semi-major axis is denoted by A. Now, if we held the line of apses in place, and then so we're holding this line in place, and then we shorten the line of the minor axis, the orbit would flatten out. So let's say our minor axis actually went up to here or something. So if we shortened it down to here, you'd see that if it was here, the orbit would be like this, would go, oh, hold on. Can I have a pointer here? I'm not sure. Yes. Mm, I'm not sure if how do I have a pointer? Okay, give me 2 seconds.
There should be a pointer at the bottom left corner if you're using PowerPoint presentation.
I'm not using PowerPoint directly. I'm using the Zoom uh function to okay. I just Googled it and it said I should look for annotate in the toolbar, which I'm not seeing. Yeah, I'm not seeing this toolbar. I think we'll just have to carry on without. Mm, apologies. Okay, yeah, can't see it. Sorry. Um, so yeah, where was I? So yeah, I was explaining the the size. I just finished explaining the size, which is indicated by the so where you see A, the gray like bracket, that's what we call the semi-major axis. That's half of the major axis. So from the arrow at the end of that to the other arrow on the left side of the sun, that whole distance is our major axis. Now, if we held this line, which is the line of apses, if we held it in place and then we shortened the line of the minor axis, I was saying, the orbit would flatten out. So, where you see the minor axis written there, that shape, that elliptical shape of the orbit is indicated by B, which is our minor axis. So if we elongated B, we would get this blue dotted circular orbit. So at this point, our uh B would be equal to the size to the length of our semi-major axis. So this shows us that the minor axis determines the shape of our orbit. So the second parameter is what we call eccentricity, and it's denoted by E, and it's related to the radius of the periapsis and the radius of the apoapsis and the length of the major axis, because from our apoapsis length and plus our periapsis length is equal to the major axis. So that's where you see the equation on the right side of the screen. E is equal to RA minus RP over RA plus RP. And then our semi-major axis is RA plus RP over 2. So now, in this image, we see two planes intersecting with the Earth. The blue plane is the equatorial plane, and the yellow plane is the orbital plane. And this is the orbital plane of the red object that is orbiting the Earth. So this red object, we'll just call it a satellite. So on the equatorial plane, we see an arrow pointing towards us, right? It's pointing to some arbitrary position in space, and this is what we're going to take as our reference point. This is normally the reference point taken as the vernal equinox. So at the intersection of the two planes, we see that there's a line that joins them, and that line is called the line of nodes. So in this slide, we just talked about this line where the major axis, that's the line also called the line of apses that joins the periapsis, the point of the periapsis and the point of the apoapsis. So in this three-dimensional visualization of it, this line is the same. Not the same, but has a similar connotation. So this line is called the line of nodes. And it's so called because there are two prominent points or nodes where the orbits intersect. So if we look at the orbital plane, which is our yellow plane, if we look at it from below and we trace counterclockwise, we see that the point where it intersects with the equatorial plane, um, it starts to go above it or ascend it. So that's this point, this green point is what we call the ascending node. So if we keep tracing that orbit, we see a point on the orbital plane where it intersects with the equatorial plane again, and then it starts to go below it. So that point where it intersects or starts descending beneath it is what we call the descending node. Now, if we hold the equatorial plane and the line of nodes in place, and we move or tilt the orbital plane, we see an angle between the two planes change. So we're holding our equatorial plane in one place, we're holding our line of nodes in one place, and then we move our orbital plane. Um, this changes the angle between the equatorial and the orbital plane. And this is our third parameter that helps us understand the tilt of the orbit, and it's called inclination, denoted by the I. So this inclination is measured in degrees. Now we have three parameters. The first one was the size, what helps us determine the size, which is the semi-major axis. Then what helps us determine the shape, which is the eccentricity. Now what helps us determine the tilt of our orbital plane, which is our inclination. So the inclination is the angle from our reference plane, which here is the equatorial plane, to our orbital plane. So now, if we hold the equatorial plane in place again, but this time we don't hold the line of nodes in place, okay? We hold this North Pole axis line in place. We hold it steady, and we hold the equatorial plane steady, and we twist the orbital plane. We see that the nodes shift. So the descending node and the ascending node that we identified earlier, they shift positions on the equatorial plane. So they're still on the equatorial plane, but they move slightly. They rotate. Yeah. So this shift changes the angle between our vernal equinox. Does somebody want to ask something? No? Okay. So this yeah, this shift changes the angle from our vernal equinox to our the line of our ascending node, right? So this angle from the vernal equinox to the ascending node is what we call, it's not the line, the angle is what we call the longitude of the ascending node. So it's denoted here by this blue omega sign, this big omega sign, and it's me also measured in degrees on the equatorial plane. Now, we have 4 parameters to help us define the orbit. Now, we want to find the position. Now that we know that we can get the size of our orbit, we can get the shape of our orbit, we can get the tilt angle and the twist. That's the orientation, what the vernal equinox is. So, can you please explain what the vernal equinox is? I'm just gonna say it's an arbitrary point in space that we like to take as a reference position. Um, I don't know the actual, I think it's something to do with like when the sun crosses the equator or something. I'm not very sure about that, but you don't have to think too much about that. Just know that like it's the point that is normally taken as the reference axis so that we can then calculate. Let me go back here. So that we can calculate the distance from this so that we just have a reference point that we can calculate from here to our ascending node. Okay. But the actual like details of it, I would have to research and let you know. So now that we have those parameters, by the way, this will end in 10 minutes. So in like 5 minutes, I will restart this. So now we have these parameters. We want to find the actual position and the actual location of our satellite. So here, this red circle indicates the satellite, right? Here, it's changed to a black circle. So I just want to say that. So if we hold our line of nodes, um, if we hold our line of nodes, our inclination and our planes steady. I don't know if this image has I don't know if this image has gotten a bit more confusing, so I'm gonna go back and just explain with this image. I think I prefer this image. I don't know why I used the other one. Okay, so if we hold our line of nodes steady, right? And then we hold our inclination steady. So the inclination is fixed now, and we hold our planes steady. We can see that the point of closest approach, that's the periapsis. This is indicated by this red line here. This is the line. This is the point of the periapsis. Um, and the point of the furthest approach, which is the apoapsis, so it's like the opposite side of that, from the center of the Earth to the orbit, will change. But if we change the size and the shape of our orbit by changing the semi-major axis and the eccentricity, the position of our periapsis will change. Okay, so we're holding the inclination is fixed, the planes are fixed, but now we're changing the size and the shape of the orbit. So right now we see that the ellipse is going kind of like uh diagonally. Yeah, with the periapsis and the apoapsis on a line like facing towards kind of like the right. So if we change the semi-major axis and we change the eccentricity, it would we would sh change the shape of our ellipse, right? So the point of our periapsis and the point of our apoapsis, those positions would change. So the angle in the orbital plane between the line that joins the center of the Earth to the ascending node to the line that joins the center of the Earth to the periapsis is what we call the argument of the periapsis. Now let me go back to this image. Okay. So this angle in the orbital plane determines the location of the periapsis and is denoted by a small omega measured in degrees in the counterclockwise direction. Um, so this yellow plane and this gray plane, we're saying that this point is this point where they meet, that's where our like periapsis, that's where our ascending node is, right? Because it's ascending from that direction. Now that blue line is what is indicating our periapsis. Sorry for not labeling it, but that blue line is what's indicating our periapsis. So the angle from the ascending node to that blue line is what we call the argument of the periapsis. And that's measured in the clockwise direction. Now that we know where the periapsis is, we can see that from the point that joins the center of the Earth to the periapsis, to the line that joins the center of the Earth to the center of the satellite, there's another line. There's another angle, right? This is the sixth element. So this is the position of the body in the orbit itself, and it's known as a true anomaly. So first we get the argument of periapsis by measuring the angle from the ascending node to where the periapsis is in our orbit, right? Then we get the true anomaly, which is the actual position of our satellite by measuring from that periapsis point to the point of the satellite, the position of the satellite. So this sixth element, our parameter true anomaly, is denoted by nu, which is kind of it looks like a V. The Greek nu looks like a V. So in the next few slides, I'm going to be using F because this true anomaly is normally taken at a certain point at an epoch. The epoch is normally just a word, fancy word for the start time. So what we normally take the true anomaly at a certain time. So I'm going to be using F of T1, T2, T3 in the next few slides. Okay, before we move on, can we please start over? Because it says 3 minutes left. So I'm going to end and then restart. Thank you very much for telling me. So yeah, let me just rehash. We now know how to define our orbit. Now we want to move within our orbit. We want to determine different positions of our body at any given time. So we need two new parameters, the eccentric anomaly and the mean anomaly. So the mean anomaly is gotten when we draw the circle of an elliptical orbit. So we have our normal elliptical orbit, but then we draw the circle of that, the auxiliary circle that we like to call it, and we have this center 0. So please just look at this image with the yellow shading. So the center point is 0, and there's a focus F. And if we draw a line perpendicular to the semi-major axis that intersects at our point at A, that angle that angle is called our eccentric anomaly. So where our body is in the elliptical orbit, that line to where it is in the circular orbit, that from our major axis, that angle is called the eccentric anomaly. Now, for the mean anomaly, it's the angle between the periapsis and the position of an imaginary body that orbits in the same period. So in the same amount of time. as the real one, but with a constant velocity. So this is the mean motion. This average angular velocity is a constant velocity, and it's called the mean motion of the real orbiting body. So the angle of this mean anomaly is measured from the body being orbited in the direction of the orbital motion. Yeah. So this is shown by Kepler's equation. I wanted to go further, like properly talk about how this was derived, but too much time. So in the last few slides, I have references that you can check out to see how these formulas, these equations were derived. So Kepler's equation relates our mean anomaly to the eccentric anomaly. And our eccentric anomaly is related to by our this F here is our true anomaly that we mentioned in the previous slide. So when propagating, we could try to solve from the mean anomaly, uh, from the true anomaly, sorry, to the mean anomaly directly. Because when we're solving, as you'll see later on, we actually repeat steps because like through the algorithm, we repeat steps, but we're going backwards. So if you're given like a position and a velocity, from there you can get the orbital elements, and then from the orbital elements you can get the mean motion at a point, at that point that you've been given, and then from there you can get the mean motion at your desired point, right? But not mean motion, sorry, mean anomaly. But from that mean anomaly back to true anomaly so that you can get the orbital elements at the new point. It's not always so uh correct. The error margin is far larger when going from mean anomaly to true anomaly. So that's why we have this eccentric anomaly in between as a go-between, because it makes the error reduce. So these are just equations that I'm not going to explain too much, but when you're given the orbital elements and you're asked to find the position and the velocity, once you get the true anomaly and you know your semi-major axis and you know your eccentricity, it's very easy to just find the orbital radius, right? So then from that, you can then just find your velocity. So this V is velocity, because our mu is just our the gravitational constant of the body. So it's just the mass of the body times the gravitational constant of the universe. Now, this is where it gets a little bit tricky. So if we're given the initial position and velocity vectors, and the time of an object in orbit, and we're asked to find the position and velocity of that object at a later time in its orbit, there are specific steps that you should take. So the first step is to use the true anomaly. Okay. The first step will be to use the true anomaly to get the eccentric anomaly. Then use the eccentric anomaly to find the mean anomaly. So I'm saying like here, true anomaly is f of t1. So you were given an initial time, let's say 3 p.m. on some arbitrary date, right? And you're asked to find the position and velocity of the body in the orbit at, let's say, 6 p.m. or something, you know? So this T1 is our initial time that we've been given. So step one, use the true anomaly at T1 to get the eccentric anomaly at T1. Then use the eccentric anomaly at T1 to find the mean anomaly at T1. And I don't want to go through I didn't specify the equations here because they're back here. And I'll still talk a little bit about that later on. So the next step is to determine the mean anomaly at T2. So using your mean anomaly at T1, you can determine your mean anomaly at T2. That's your the time that you're interested in. So the way you do that is just by adding your n. N is your mean velocity, mean orbital motion, right? Yeah, your mean motion. So your mean anomaly at T1 plus your mean motion multiplied by the change in time, the time difference. That's how you get your mean anomaly at T2. Now you use this mean anomaly at T2 to find the eccentric anomaly at T2. And there is no analytical or closed form solution to find eccentric anomaly from the mean anomaly. So this is normally done through iteration. Then, using your eccentric anomaly at T2, you find your true anomaly, which is the actual radial position, right, of the object in the orbit. And then you use the orbital elements that you were given in the first place, and now your T2 to calculate the new position and velocity vectors. It's a bit much, but don't fear. So in this sequence, I talked about iteration. So after you get from your mean anomaly at T1 to mean anomaly at T2, to get back to eccentric anomaly, you need to iterate. So I'm going to now explain mm, Newton's algorithm for iteration, for when you can't find an analytical solution to a problem, right? So generally, to find the root of a problem, you take an initial guess. So Newton, let's say you have a function, right? You have an equation that you can't solve. So you take an initial guess. You can take an initial guess as 5, as 6, as 10,000, as 0.7. It doesn't really matter. Then you approximate the function of that equation that you're trying to solve, right? So uh this f of x, so let's say you're trying to solve for x, right? And some x is just some polynomial equation or something. So your f of x is approximately equal to the new f of x plus the derivative. Sorry, let me not confuse you. Your new f of x is approximately equal to your f of x currently plus the derivative of the function of that current x f of x. Then the delta, the difference between the actual value currently and your guessed your initial guess. Okay. Then the third step is to solve for for that new value of x. So when you equate it to zero, when you equate that equation to zero, you then solve for your new value of x, and you get x minus f of xn over f prime of xn, right? So then step 4 is to update your guess. So now that you have this new value of your x, you're probably still thinking, oh, I don't know if this is the actual solution. So what you do is you find the delta again. You find the delta from this new value and the old value, and then you update the equation. So you keep doing this and iterating in this way until the function, the difference of the difference of the absolute of that function is very, very small. Is less than the tolerance that you want. Like let's say I only want an error margin of 0.001. You keep going until your error margin is at that point, and then you stop. So that's how Newton's algorithm is. So if we want to apply this to Kepler's equation, which relates our mean anomaly to our eccentric anomaly and our eccentricity. Normally, we don't have a better option. So normally we take our initial guess as our mean anomaly because we already know our mean anomaly, right? So we normally just take the initial guess of our eccentric anomaly as our mean anomaly because we're given M already, and we want to solve for E. So you take the function of the equation. Our equation is M is equal to E, capital E minus eccentricity sine eccentric anomaly. So you take the function of this, you equate it to zero, and then you uh, take the derivative, and then you just plug it into the equation. So to get your new value um, of your eccentric anomaly, you do your initial guess minus the function over the derivative of that function. And then this is what we get, right? We get En, our current guess of E, is equal to our initial guess of E minus initial guess of E plus eccentricity sine initial guess of E minus mean anomaly all over 1 minus eccentricity cos initial guess of E. So at this point, like E, and M are the same, but because you can't you don't have to start with the mean anomaly. Like you don't have to start by initializing it as the mean anomaly, but it's just what we do. So you keep going until the absolute of the equation is less than whatever tolerance you want. Okay. So now that I have explained that, we will move on to an example. Now, when I was doing these slides, I I also didn't even manage to finish it. Um, like I could have finished it if I was solving with my hand, but because I was doing it with code, I still got a little bit stuck because I got only up to implementing this algorithm. So I guess we'll see where we get up to during the code. So now I have already pushed the slides and um yeah, the slides and the assignment to the GitHub. So there's no code. I haven't pushed any code to the GitHub today. So we'll just be doing it together. Let me share my screen. Okay. Okay. So if you haven't already, just open up to where your Python for orbital mechanics folder is. Go into code and create a new file. Initially, what I wanted to do actually was I was creating another file in here in the standard library. I wanted to call it it's called standard tools, where the function that does this the algorithm that does performs the algorithm will be in the standard tools file, but I didn't end up finishing it. So probably when I do, I will push that and then you can just like reverse engineer it. But we will just be doing it within the same file today. So not in your standard lib folder, but in your code folder, create a new file. I'm just going to call it codes for classic orbital elements and codes example dot py. Okay. Does anybody have any questions before I start? I don't know if I explained to the best of my ability. So if you have any questions, do let me know so I can answer them before we start the okay. No questions. Okay. I'm no longer sure. I don't know if I can't double share. I don't have two screens right now. So I'm just going to explain with my mouth. Let me first have all the Okay, so in the equation we were given our Okay. In the example, we're given a question that says a rocket is in an elliptical orbit about the planet Kerbin. This is actually from somebody created this question from the game Kerbal Space Program, if anybody has heard of it. It's a very good uh it's a computer game to help understand how to like plan trajectories and orbits. I would highly recommend if you have the time or the space on your laptop. So a rocket is in an elliptical orbit about the planet Kerbin. Calculate the position of the rocket 15 minutes after periapsis. You're given that A, the semi-major axis is 2,160 kilometers. The eccentricity is 0.832, which means it's very elliptical. And then the mass of the planet is 5.29 times 10 to the power of 22 kilograms. So those are our initial conditions, A, E, mass, and time. And we're asked to calculate the position of the rocket after that elapsed time. Okay. What's today's date? Today is 8? No, 9. So we're given that A is equal to 2160. And we're going to be calculating using meters. So I'm just going to automatically just add the 3 zeros. So this is our semi-major axis in meters, right? Then we're given the mass of the body, 5.29 times 10 to the power of 22. That's the mass of the body in kilograms. We're also given our eccentricity as 0.32, 0.832, right? Eccentricity. What else were we given? We were given the time, right? Time elapsed. We were given 15 minutes, but when we do the calculations, we calculate in seconds. So 15 minutes, 2 seconds is 900. I could just put the equation, but I'm just going to put 900. Time elapsed in seconds. What else were we given? Those are the 4 parameters that we were given. Yes. Um, Now let's just state our constant that we know that we'll need at some point. The universal constant of gravitation, that's 6.67 times 10 to the power of minus 11. Yeah. So state of gravitation. Now to calculate our mu for our body, just do G times mass, right? Kerbin mass. Kerbin grav const. And this should be in kilometers cubed per second squared. What is the mu? Mu is each body has its own gravitational constant. So in the equation, I think Newton's second law, that's F equals ma, right? Was also rewritten as F is equal to G times the mass of one body times the mass of our second body all over r squared, the distance between them squared, right? So um this the mass and g gives us like the a gravitational constant. So if we know that like this body is gonna be stable, let's say like we have like the sun and we want to calculate the force of like all the other planets. We know that these two, this G times this M1 is gonna stay the same, right? So the sun itself has its own mu. All bodies in the universe have their own mu. It's just the gravitational constant times the mass. So it's normally denoted by that weird U with the long line on the left-hand side, the Greek mu. So that's what mu is. It's just the gravitational constant that times the mass of the body. Okay. Yeah. Then we're going to need what else? We're going to need our the orbital period. The orbital period is the time it takes for the rocket to go from one point in the orbit back to that same point. Like, how long does that take? Like, the Earth takes 365 days to orbit the sun. That's the orbital period of the Earth. But, like, Saturn, I think, takes like 88,000 days or something like that. No, not 88,000. What am I saying? The closest planet to the sun takes, is that Venus? I'm not sure. So bad. Takes 88 days. So that takes way less time. Its orbital period is way smaller than the orbital period of Earth. So we're going to calculate the orbital period of our rocket around Kerbin. So that is given by 2 times pi, 2 pi times the square root of our um semi-major axis cubed all over mu. So 2 times, we're going to need pi, so let's import math as m. So m dot pi times m dot, we want to square root, right? Square root of our semi-major axis cubed, right? All over our mu, our gravitational constant. Okay, so this is what the orbital period of the rocket around Kerbin. And this orbital period is normally like when people define it, you'll see that it's normally like defined in years, but I think this is gonna be in days or something. This ends up in days. I think. Not 100%, but I'll just leave that there for now. So now we've calculated our orbital period. We know the gravitational constant. Let's calculate the mean motion. So the average angular speed of our rocket, that is the mean motion. So 2 times, I think it's 2 times pi over t. Yeah, 2 times m dot pi all over our orbital period. That's how we get mean motion of the rocket. And this is in radians per second. There's going to come a point where we're going to be doing a whole lot of conversions, so be ready for headaches. Okay. Now, the mean anomaly is given by mean motion times the time, right? Times the time. The time it takes us to get to this point. So that's our mean anomaly. Then our eccentricity is already given. Uh, okay, now let's define our functions. Okay, so def, I'm just gonna call the function of the equation Kepler because it's Kepler's equation. So let's just do that. So Kepler takes what do we want to do? We just want to return the formula, right? So this is just the function. So we said that our our equation was m is equal to, what was our equation? What is n? N is the mean motion of the rocket. N is the average angular velocity. Like, how fast is this rocket going on average? Because the velocity changes at every point in time, but we don't want to know the average speed. Like, if we sum up all the velocities and divide by all the time it takes, that's our mean motion, our average angular speed. Yeah. Okay. Where am I? Back to our equation, right? Yeah. So m is equal to e, I think minus e minus e sine e. That's our equation, right? Sine big E. That's our equation. So when we take the function of this, when we equate this to 0, this m is going to move over, right? So this m is going to become minus big M is equal to 0. And then that's going to become a function. That's our new function. So it's going to take these three arguments, right? These these three parameters are what the function is dependent on. So first write the equation in here. X. I'm not supposed to do that, but so all we want to do is we want to return this equation. We don't really want to, there's nothing for us to calculate really. We just want to return this equation. So E, oh, I got that wrong, sorry. Not minus, it was plus. E plus our eccentricity times sine, math dot sine E minus our, we don't need this, minus our mean motion, right? Yes. Yeah, I think that looks good. Why am I getting like an underscore here? What's this for? Oh, yeah, because I haven't defined that this is going to take those values. So it's going to take E, eccentric anomaly, it's going to take eccentricity, and it's going to take mean anomaly. So that's all we're going to do. So what does this function do? This function defines the function of Kepler's equation. Okay, so now that we have um our function, we need to have the derivative of the function, right? Because we need to know the difference, the ratio between them. So we're going to have another function, Kepler derivative. Kepler deriv. This is also going to take our eccentric anomaly. But this time it's not going to take the mean anomaly. It's only going to take the eccentricity, right? So again, we only want to return 1 minus eccentricity times math dot cos, because this was already stated in the slides, cos our big E. So what does this function do? It defines the function okay, okay, that's good. So now that we have the function and the derivative of the function of the equation and the derivative of that. What? Deriv. Now we actually want to implement Newton's algorithm into that. So let's define Newton's Newton's algo. Newton's algorithm. So what does this algorithm need to take? Well, when we defined it, we said you take to get your uh estimated, like your next value, you first need to take this initial guess value minus the function over the derivative of the function. So definitely it's going to take the function. So let's just say f for function, it's going to take that. Then it's going to take the derivative, which is f prime of that function, right? So let's just call another parameter f prime. Then it's also going to take the guess, right? The initial guess and then the next initial guess. So every time we iterate, every time it goes through this algorithm, the guess is going to be changing. So let's just call that parameter current guess, which will start from the initial guess. And then we also need the tolerance, right? Like uh how close to the actual solution do we want to get do we want our answer to be? So let's state the tolerance. Could do 0.001. I think that's a bit, actually, might be too small. Okay. Um, so what does this function do? This is Newton's method of root solving. So we're trying to get to the root of the solution. Variable functions. Okay. So we don't necessarily need this, but let's have a step counter so we know what step we're on. Like every time it goes through, we know how many times it's gone through um this algorithm. So let's have a step counter. Then our delta f, the ratio of the function and the derivative, we're gonna call the delta of functions. F is equal to f is our function, right? This function that we're going to input into Newton's algorithm. So this function will be our Kepler's function here, right? So this f prime is going to be our Kepler's derivative. So our delta f is equal to the function that takes the current guess. It takes the current guess, which is our e, right? This e here. That's our initial guess. And then the next time it's going to take the next initial guess, which is what it's going to have calculated before. Um, and then it takes these two values. So because these values are the same, I'm going to create another variable called arguments. It's gonna have our E and our M. So let me change this. Args equals. So now we within our args tuple, we have this first value and this second value, so that I don't have to keep writing E and M, E and M. Um, I'm just gonna have args 0 and args 1, so I can just identify which one I'm stating. So here would be args 0, right? And then this one would be args 1. Then here too, let's just change this to args. Uh, this E, not this E. this eccentricity would be our arcs, the 0th value, right? Yeah, so let me also add it here. Okay, this is gonna restart again now, so let me stop here for now and pause this. Okay. Can you guys see this annotation here? Pi times 2. So it seems I can annotate here, but I can't annotate in the other place. How do I erase? Okay, no more annotations. Okay, thank you. Okay, where were we? We were at our current, defining our ratio. The ratio, let me just state that here so we know. We're calculating the ratio, function, and the derivative. Okay, so our function takes in the current guess, so we know that this function definitely, okay, apologies. This function definitely takes in this our current guess E, and then it takes these other parameters, eccentricity and mean anomaly. So our function here is going to take the current guess and our arguments, whatever arguments that we state. Then we're now going to divide that by our f prime, the derivative, which also is going to take the current guess, and then it's also going to take arguments. Okay. So now that we've defined our ratio, we're going to start a loop that's going to go through each new current guess. It's going to calculate it, uh and then when it gets like when the absolute value of our ratio of this delta F, when the absolute value is less than our tolerance that we specified, then it's going to break out of the loop. So we want to start a loop and break out when absolute value of our ratio is less than tolerance. So while the absolute of our delta F is greater than our tolerance that we specified, our current guess, we're going to take the ratio from our current guess. So our current guess so it's going to be our current guess minus delta F. But to simplify this, we can also just write it like this. So this does what? Calculate next current guess. Then delta F is equal to F So we're just going to take this again, basically. We're going to recalculate our ratio because this value has changed, right? This, the current guess has changed, the ratio will have changed. So calculate new delta F. And then we can also just count uh the step. So the new step will be the old step plus one, right? So okay. So now we have implemented our algorithm. So what is the next thing to do? So in our steps, I also realized when I was going through my other video that I think the screen might have been too small. So please, if you can't see what I'm writing, do let me know what I'm writing, what I'm typing. So, okay, so after we go through this algorithm, which we've just implemented, right? So we're going from here to here. Um, we iterate, and then we need to find our true anomaly. Okay, you just zoom in on your side. Okay, got it. Yeah, we find our true anomaly, and then from the true anomaly is where we can find our position and our velocity. So let's go back to the code. So let's define true true anomaly. Well, time's almost up already. I think I said these classes were 1.5 hours. Um, so our eccentric, so if we implement this algorithm, we can get our eccentric anomaly. Wait, did I return anything here? No, I didn't. Should it not return the values? Yeah. Okay. Uh, yeah, eccentric anomaly. Our new eccentric anomaly is an unknown. Um, sorry. Return current guess and our step, right? Yeah. Okay, so it's going to return two things. So we can get our step and our actual value of our eccentric anomaly. by implementing Newton's algorithm, right? So within Newton's algorithm, we're going to put in our Kepler function, and then we're going to put in our Kepler derivative. What else did we say we needed? We needed our current guess. Uh, our current guess, let's say E naught is equal to, I said we should put it to mean anomaly, but I'm going to put to mean anomaly minus E, minus eccentricity. So that's our current guess. So let's input our current guess here. Our initial guess. Then our tolerance is, let's say 0.0. This is already stated. So when this runs, it's going to have this tolerance. But if you state another, let's say another tolerance, it would override that. So if I don't put anything here, it's automatically going to take this value. And then we stated that it has arguments, right? And then we have our args here. So args. Okay. So we get true. I want to go back to this equation. Okay, this is our eccentric anomaly, right? So E is equal to 2 times arctan of the root of 1 minus E over 1 plus E times tan F over 2. And our F is our true anomaly, right? So we're now trying to go from mean anomaly, eccentric anomaly to true anomaly. So we have our eccentric anomaly. We've calculated this. Now we want to go back to our true anomaly. So it's the same exact equation actually. Same exact equation, but we just swap the E and the F to get the true anomaly. Okay. I don't know the actual name of that 1 minus E part, and I don't want to Google it, so I'm just gonna call that ec for now. Because I know it's not eccentricity, but ec frac, let me call that. Because I don't want to like write the whole equation in one place. So I want to like separate it into bits. So 1 minus eccentricity all over 1 plus eccentricity, right? So it's like 1 plus eccentricity. So the other side of it was f over 2. Like, because we're going to do root of this times times tan of the eccentric anomaly over 2. So let's do half eccentric anomaly is equal to eccentric anomaly over 2. Then our new value, which was our f of t, our f of our what do we call that again? New is a true anomaly. Yeah, sorry. New, yes, is 2 times arctan. So let's use math dot arctan. Uh, then within that, we're gonna square root, right? Math again, dot square root of our ekfrak that I don't know the name of times the tan of uh, half. Yeah. Does this look correct? Yeah. So this true anomaly now is just going to return out new value. Okay. So now that we have our true anomaly, we're going to use that to get our position and let me go back. So now I have to keep starting this from the beginning. So I stated that these two equations we can just plug and play basically. So our now that we have this value, we have this, we can now get this. So this is our new that we just calculated. We can now plug this in. And then uh once we have this, we can then get the velocity. Okay. Okay, back to the code. So actually when I was trying to do this, I really only actually got up to the finishing this algorithm part. I didn't really finish this. So we're doing this together now. Def, what did you call it? The polar equation? Polar equation. And this one is going to uh return the radial, the radial value of the position of rocket. Right. And then we're also going to have the vis viva. Vis viva. That is also what we're going to use to help us get our uh new velocity. Velocity at uh the elapsed time. So let's go back to this equation. The equation is the radius is equal to a into 1 minus e squared, right? So I think we've defined that as a semi-lattice rectum before, the a into 1 minus a into 8 times 1 minus e squared, right? Um, and then this is actually our 1 plus e cos f of t. Was that here? Yeah, it was this, right? But we're just going to write it as it is. So new deriv, I'm just going to call it 1 plus e times m dot cos um this, right? Mm. Wait a minute. Can I do that? I don't think I can. But let's see. And then our R is equal to P over the then return R. I'm sure these two are supposed to take. This is supposed to take in the true anomaly is dependent on this. Mm, now let's move on to this one. Now our velocity is equal to root of mu. We already have our mu. Mu. I don't think I want to write it all in one, but let's see how it looks. Square root mu into, wow, this is gonna look very uh messy. So I'm gonna have this like this minus, because it was 2 over r, right? 2 over r minus 1 over a. 1 over a. And our r is here, so let's just r is equal to, let's run the polar equation. Okay. Yeah, and this basically, yeah, root mu times 2 over r minus 1 over a, return v. So we get the velocity. So now we have our rate, our position and our velocity. So let's try and run it. Oh, I hope this runs, man. I'm not gonna cry, but I don't want it to be a running tradition that the code never runs while we're actually doing it together. So what's that? If, if no name. Oh man, I hope this runs. I hope this runs. So first we're gonna solve for so now that we have the functions to help us do the calculations, now we're gonna try and run them. So we're gonna first solve for eccentric. No, but we already solved for eccentric anomaly, right? Yeah, we did to get the true anomaly here. Um, okay. So since we already put it in here, I'm just going to run this. Solve for true anom, get position and velocity. So I'm just gonna run true anomaly. I'm gonna run polar equation, and I'm gonna run the Vis-Viva equation. Oh, it's called Vis-Via. It's Vis-Viva. That's the name of the equation. I don't know why. Oh man, oh man, oh man, oh man. Okay, so what does this give us? This gives us position. Uh, position. And this gives us velocity. Right? I'm kind of scared to run this. Ah, Rishav. Yeah, okay. So now we're gonna print to the screen the answer that we get, right? So, position, position is what are we gonna do? Where's my percentage sign? Position is position is an integer, right? Or is it a float? It should be a float. Um, and velocity is oh my gosh. I think this sounds like mm, position is in meters, right? And then velocity is in meters per second, I guess. Because we're not doing kilometers per second. Okay, so the percentage sign, position, comma, velocity. Oh, I just have a feeling it's not gonna work. Why am I so scared? Okay, let's try and run it. Close sample dot py. Am I in the right folder? Yes, I am. Oh, index out of range. What line is this? Line 22? Mm, oh, let me see if I put the bracket. If I put a bracket around here. Mm, this is 0, 1. This should. Oh, I might actually cry. Mm, does anyone else see any error here? I'm Googling list index out of range. Oh, but this has 0, 1. So this isn't out of range. What if you just use E and M for themselves instead of arcs. Okay, okay. Oh, I'm gonna have to go back to all of these. Okay. I'll just comment this out and then yeah. See, Control Shift F, right? Replace. Mm, if you see arcs. No, I have to do it one by one. So E comma M. This is M. This is E. This is just E. E comma M. Hmm. Why do I have this? Let's see if this runs. Redefining. Oh, thank you. Thank you, Ahmad. But now I've gone and erased them all. Um, but let me try and save this. Hmm. Now I have a different error. Control Z. That is true. But about the redefining that you mentioned, I think like here I have to state that it's a tuple, no? No. Okay. Yeah. Uh, yeah, I kind of have to state that it's a tuple because if I don't, will this be able to run? Okay, let's see. Oh my Lord. But now I'm getting the exact same error, even though I put two different things. Like this, this is the same kind of error, no? Yeah, it's the same error. The non-default argument follows default argument. Okay. Oh, I see. Mm, you're telling me that if there's a default value, so Newton's algorithm, when I do this, it should be like this. Yeah, never mind. This should stay the same since I didn't implement it here. Okay, I think I know what you're talking about now. Wow, it worked. We solved it. Wow. Why am I so surprised? Oh my gosh. That makes me so happy. I don't know. Yay. Oh, cool. That is actually so cool. I'm happy. I'm happy. I'm very, very happy. Okay, so we got our velocity as 4,192 and our radius as so this is our position and this is our oh my gosh. Huge round of applause for everybody, guys. I'm so proud of you guys. I'm so proud of all of us. Wow. I really didn't think it was gonna work. Okay, cool. So yeah, if you weren't running at the same time, please try to run it and um yeah, if you get in any trouble, let me know on the WhatsApp group. Um yeah, that's the end of this. So let me show you the um oh, Samuel's ran. Okay. Yay. Cool, cool, cool. Um I want to show the assignments. Be- I also wanted to, while I was trying, I think what I wasted a lot of time on actually was I was trying to like change in the last assignment there was a question that said you could simulate universe 3D. So I spent a lot of time trying to do that, even though that kind of had nothing to do with this class. Um so hopefully if I manage to get that working, the next thing that we're going to go into, which is coordinate systems, we may be able to actually simulate that in 3 dimensions, hopefully. But this is the next assignment. So 3 different levels of questions. This second question, I think, well, I think you can still attempt it though. But where I got it from, they were doing a whole lot of conversions from like different coordinate systems. So I was very wary to put this question in, this orange question, but I think you can still attempt it with this software that we just built. So these are the assignment questions if you want to try them out. Uh, thank you for joining and yeah, I hope to see you next week. Does anybody have any questions before we finish? Zoom is already telling me there's 2 minutes and 30 seconds left. So does anybody have any questions within this time? Nope. Okay, then I'll just end here. It's past my bedtime, so I'm just gonna go to sleep. But wherever you guys are, good morning, good afternoon, and good night. Bye.